Hey guys, welcome to this video on the Wavy curve method. In this video, I want to explain you and talk to you about the Wavy curve method and show you the beautiful nature of the number line and how you can use the number line to solve inequalities. And I want to give you the intuition first and then build up to the actual mathematical formula of the Wavy curve method. And one driving force behind me making this video is that I actually tried to find a good resource by just googling about this, and I was really disappointed by the actual results that I got, because most of them just refer to a basic mathematical formula that you will see in most reference books. They don't give you the detailed information and tell you about uh, the inspiration behind the wavy curve and what it really is. They'll just throw a formula at you and show you 2-3 solved examples, but that's not what I want to do in this video. I just want to take one simple example and show you what the wavy curve actually is. So without me wasting a time, so let's just jump straight to the method. Sorry, so I want to go to the second screen here. This is the learning graph that you need to know. So basically all you need to know right now is that polynomials and basic inequalities are the only prerequisites if you want to follow along this video. So if you want to learn wavy curve, you need to know polynomials and basic inequalities. And learning graph concept is actually very important, but I'll make a separate video and explain to you this learning graph. Okay, but not so important here. So I have a function f of x, which is x minus 3 times x plus 2 times x plus 5 divided by x plus 1 times x minus 7. I want to figure out in what intervals this function is positive or negative or 0. How can I do that? Well, we can make use of the good old number line. So let's draw that. I want to attempt to draw a straight number line, so let me see. So there you go, a number line obviously extends in both directions to infinity. Let's start from here. 0, 1, 2, 3, 4, 5, 6, 7, and I want to go 7 units in the negative direction. So minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, and we are almost there, minus 7. Okay, now all those values in which this function is 0 are definitely the roots of this function. So just by looking at the function by looking at the function definition, you can see that 3, minus 2 and minus 5 are the 3 roots, and I want to plot the 3 roots by my favorite color, orange. So let's Control Z, not working here, so let me okay, so 3, where's 3? Here's 3. I want to darken this. Minus 2, and then minus 5. Here's minus 5, here it is. These are my 3 roots of this function. I also have this additional information about these points in which this function is undefined. So 7 and minus 1 are the 2 points at which this function is undefined, and I also want to plot these points. Now the representation is generally a outlined circle, so or the outline of a circle. So let me draw that here at minus 1 and at 7. Okay, so what can I conclude, or what I can do with this given set of data, and how can I make use of this given set of data to actually solve the main problem that we have? Well, let's consider all the numbers which are greater than 7. So let's say that Well, there are two ways you can think about this. You can pick a specific number like 8, which is definitely greater than 7, or you can just uh, say like you can take any number in general which is greater than 7, and then when you look at the sign of the numerator, so it's going to be, let's say we take 8. 8 minus 3, which is 5, it's positive, and then these two terms are definitely positive, so the numerator is positive. Now if you look at the denominator, 8 plus 1, 9, positive. 8 minus 7, 1, so denominator is also positive. So I want to make a table here so you can understand what I am saying. So in the first column I want to write the number that I am taking, and then sign of the numerator, sign of numerator, I'll just write NUM, sign of denominator, and then finally the sign of the function, sign of f of x, and I'll just draw lines to separate columns. Okay, so the first number I'm taking, which is greater than 7, sign of numerator as well as the denominator in this case is positive, therefore the sign of function is positive, because remember, when you divide a number which is positive by another positive number, you're going to get a positive number. And we are only concerned about the signs of function f of x and not the magnitude, because remember, we are only finding the intervals in which this function is positive or negative. We are not finding the actual values of the function at those specific points. So now let's look at this interval from 3 to 7. Let's take any number in this interval, let's say 4, and when I take 4 and I input into this function, you will see that the sign of the numerator is positive, so this is positive. Sign of denominator is also, no, the sign of denominator is actually negative, so we are considering 4, so the sign of function is negative, right? And the reason I am saying that you can pick any number from 3 to 7 is because, let's say that this interval had two signs and not just one, like it had positive and negative both signs. Well, then the function wouldn't be possible, because let me try to explain to you what I'm saying. So let's say I had a function which had two roots, so these are the two roots of the function, and it looked something like this. So this function is positive between these two roots, but could it be the case like I had a function with two roots and within that interval it showed both signs, positive and negative? Is that possible? Well, let's try to see that. If it had positive as well as negative sign, you will see that it's actually not true, because it violates our assumption. Now it has 4 roots as opposed to 2. So basically what I'm saying is that you can pick any number that sits between 3 and 7, excluding 3 and 7 of course, and then you can calculate the sign of the function at that specific point, which is going to be the same as the sign of the function at that whole interval. So when we took 4, the sign of function was negative. Now in the similar way, if you consider the range from -1 to 3, so if you take any number from -1 to 3, the sign of the denominator is negative, the sign of the numerator is positive, and sign of f of x is, sign of numerator is negative actually, sign of function is therefore positive. So similarly you can do for all these intervals, and you notice one pattern here. The sign of function goes like positive, negative, like that, and this is actually a special property of these types of function. It's not the generalized rule, like you can say The sign is going to be alternating all the time. It's not that general rule, but we'll discuss more about this in the next video. But I want to continue here. So when you consider all the intervals, you will get something like this. From 7, after 7 it's positive, from 3 to 7 it is negative, and then from -1 to 3 it is positive, from -2 to -1 it is negative, from 5 to from -5 to -2 it is positive, and then all the numbers which are less than -5 are the value of the function, at those point is negative. So if you just try to connect the dots and form something which looks like a wave, it will look something like this. So this is actually a wave, and I think you realize now that's why it is called the wavy curve method. I have not really formally described the method yet. I'll do that in the next video, but I want to just recap and review what we have done so far. We were given with this problem. I want to figure out where this function is positive or negative or zero, the actual intervals. I created a number line, and then I plotted all the roots and those points at which the function is undefined, and then I considered those specific intervals like beyond 7, and then from 3 to 7 I checked what the sign of the function at those intervals was. I formulated a table, and then I created this what looked like a wave. Basically from this we can directly get our answer. So if I want to write all those intervals in which function is positive, f of x is positive, these are x belongs to, well, you can just see -5 to -2, and without square brackets, because remember we are not including -5 and -2. And then union, where's the next positive interval? Well, this is from -1 to 3, so from -1 to 3, and then union the next positive interval from 7 to infinity. So hopefully you can see the pattern here, and you can get the sense of how this method might work. I've actually not described the method. Again, I'm telling you that I'll do that in the next video. Thanks for being patient, and thanks for watching this video. I'll cover this in the next video in continuation. So again, thanks for watching.